Hi, everybody. My name is Russ Tedrick. I'm at MIT and at Toyota Research Institute. I want to tell you today about what's been relatively a long journey in my life, thinking about simulating robots that are making and breaking contact with the world and performing optimization algorithms that can optimize through contact. Okay, so I don't have all the answers today, but I can tell you that on my journey, things continue to get interesting. And I'd say some of the recent new discoveries have come because I've changed my thinking from thinking about just leg and locomotion to thinking more about manipulation. And there's also been a lot of new energy and ideas and excitement coming from the reinforcement learning community recently. And I want to just kind of tell you about where I'm at on my journey. So the slides are also available. You see the URL in the top corner. If you prefer to advance through the slides on your own or look at them or slow down, those are available for you. Let's get started. So I want to tell you about simulation and control through and optimization through contact. And in particular, one of the big questions that I'd like to address today is the sort of surprising results that we've seen from reinforcement learning that don't use analytical gradients, and whether we should really be using analytical gradients. But generally, I care a lot about robots that make and break contact with the world. And I don't mean simple contact like my foot occasionally touches the ground. I want to think about very dexterous contact interactions with, robots tying our shoelaces like this, something which is just so far beyond my ability to make a robot do anything like this, or even simulate things like this with high enough fidelity that I would trust my simulation to be faithful in reality. We're getting close, but the optimization problem feels very hard. The perception problem feels very hard. This is a great grand challenge. Okay, I'm conscious of the fact that you're watching on video this year. Hopefully next year we'll be back in person. But because of that, let me tell you what I'm going to say right now. I'll give you the punchline, and then we'll work through the details, and you can sort of decide how long you're going to stick with me. So my big messages for today. I want to talk about whether contact really implies bad optimization problems. And the summary statement is that contact can lead to discontinuous or stiff dependence on the parameters, but it might not be as bad as you think. It happens more in the corner cases. Those corner cases are important in a lot of our work, but I just want to discuss when it does matter and when it doesn't matter. Stochastic optimal control, the type of formulations we see often in reinforcement learning, can certainly smooth discontinuous objectives. And that's going to be an important idea today. But actually doing straightforward Monte Carlo approximations using analytical gradients, first order gradients, of discontinuous and stiff objectives can give bad results, okay? And I think that might actually explain some of the relative surprising success of zero order methods compared to some of the obvious, what many of us think would be obvious use of first order gradients. And there's a new way to think that we've started thinking about this using the lens of randomized smoothing from optimization. There are some other discontinuities to be aware of. So I say that maybe in the mathematical sense, contact shouldn't make discontinuities as badly as you might worry about. But actually, the way we simulate them often can lead to artificial discontinuities. And I would say almost bugs that happen in our simulators all the time. And I think it's a big question whether those are affecting our work or whether, and can we address them? I'll tell you one particular way that we've been trying to address them here with a contact model we like to call a hydroelastic contact. And I'll finish by saying that gradients aren't the whole story. I don't believe gradients will be the whole story for planning sophisticated motion through contact. We still need something that's more at the level of AI planning or search. And I'll just make a call out to some new work on global planning through contact. Okay, so let's dig in. We'll start with this idea that contact can lead to discontinuous stiff dependence, but maybe not as badly as you worry about. And let's start, kind of go backwards in time for me. So I started thinking about contact in the context of walking robots, and in particular in pretty simple walking robots. This is one of the simplest cases of a passive dynamic walker. You put it on the ramp give it a little push, it can fall into a stable limit cycle behavior, but there's no control here. It's just powered by gravity. This one's called the compass gate biped. And again, it's just falling down a ramp. The spheres are indicative of our point masses in our model. This is a very clean model in the sense that it's got a very simple mathematical description. We make approximations of the contact as just a point contact interacting with the ramp. We assume that that contact is inelastic, instantaneous, impulsive. We assume the friction is infinite. It's like the simplest possible case. And in that simplest possible case, we can think very clearly about the implications of contact and what those contacts models look like, and how do we do optimization with them. In particular, the famous result in the compass gate is that it will, as you saw, it will walk stably down a ramp in the sense that it has a stable limit cycle behavior. If you plot the angle of the left leg as it goes through that limit cycle, then it has this swinging through the swing phase, and then the foot will come in contact with the ground, and we have a discontinuous jump in velocity. The velocity discontinuously changes, loses velocity. Now it becomes the stance leg. It moves smoothly through its arc until the other foot collides with the ground. I have a discontinuous jump, and now I become the swing leg again, and I smoothly travel through that same path. It's amazing that this is a stable limit cycle even for a passive robot. That's a story you've heard before. Okay, so I see some big jumps and discontinuities there. Does that screw everything up for our optimization or not? Let's discuss. Okay. So the generalization of that basic view of the compass gate and the simple walking robots is the view from hybrid dynamics. Okay, so in general, I could take a rigid body system making contact, and I can think about, this is my cartoon robot foot moving through the air, and I have smooth trajectories when it's moving through the air. And at the moment where I have a new contact between the foot and the ground, here the heel is striking my half plane model of my ground. So the heel's position equals 0. I think of that as having a discontinuous jump and then a smooth dynamical system again that evolves in time. Okay. This is kind of traditionally, we've modeled this as just a jump discontinuity that has its own dynamics, and we know how to write those in closed form. I feel that the hybrid dynamics is super general and useful. It's just a little bit more general than we actually need for multi-body systems. There's a slightly narrower class where you think about rigid body systems with frictional contact as measured differential inclusions. So you can really think of it as a differential equation. Friction means it's a differential inclusion. So it's a set valued differential equation, and it's a measure differential equation because we have these delta functions that happen when we have contact events. Okay, but in the class of second order mechanical systems undergoing these dynamics, we understand, or we carefully model the evolution of trajectories in these systems. If you give me an initial Q for my positions, V for my velocities, then Q, the positions evolve, in a continuous way over time. There's no teleporting. We don't ever discontinuously change our position, but our velocities do discontinuously change when we have impact. If we want to say that there's no penetration and you have a velocity coming into a surface, then you must have a discontinuous change to a velocity that doesn't allow any penetration into the surface. Okay, but those velocity jumps can have, we assume they have locally bounded variation, and we can do good work mathematically with those ideas. We know how to compute analytical gradients through all this. All the discontinuities from contact, the collision, impulsive dynamics, we know how to take gradients through there. Okay, I mean, when people say we have differentiable physics because we've trained a neural network, that always sounded silly to me because we know how to differentiate through physics, all of our physics engines perfectly well. There's never been any problem there. Okay, as a result, because we have the ability to write these gradients beautifully down, we've seen for many, many years, for decades, we've seen gradient-based trajectory optimization working very well in these problems. In particular, in the case where the contact sequence is fixed. So if I know for my walking robot that I'm gonna strike with my heel first and then strike with my toe and then push off with my heel and push off with my toe, and my other foot is timed accordingly too, if I'm willing to lock in that sequence, then actually our gradients are very well behaved, and our gradient optimization works extremely well. There's been a class of problems over the last decade or so that have been called contact implicit trajectory optimization. Okay, and they try to solve the more global problem where you actually also have to decide the sequence of contacts, or whether you're making contact or not making contact. That is generally still considered a harder problem, in which we have results that are less of a technology. They require a little bit more tuning, a little bit more cost function tuning, more care by the implementer. There's many great success stories there, but it's not as hardcore of a technology yet as the fixed mode sequence. And now we've seen a great set of results from reinforcement learning. This is just one of any number of examples I could have picked. This is the one from OpenAI Learning Dexterity. It was a particularly highly popularized one. And this is certainly a rich contact interaction between the hand and the cube. And moreover, it was actually one of the reasons I picked this example is they were very clear about the emphasis of training and simulation and then executing it in the real world. So people like me went through a series of reactions, I would say, when these kind of results have come out, and they've continued to come out, right? So my first reaction is, I'm kind of surprised that worked. That seems like a hard optimization problem. And then there's kind of does that really count as working, right? I mean, so it doesn't work every time. It's not a super reliable optimization. There's a lot of brute force behind it. In fact, if I had run just a bunch of random parameter evaluations and just spent as much money on my compute and had as much patience, would I have gotten the same thing? And I think the answer is probably somewhere in between the two. I think there was a lot of brute force in these kind of results. There often is. There's a lot of hand-designed cost function tuning. But there's also something, I think very good happening here. And I think it warrants investigation. I think the clean theory that we know and love and the limitations we understand need to be married more carefully with some of the success stories we're seeing from empirical reinforcement learning and robotics. So let's think about the implication of the continuity argument I was telling you about with the kind of optimizations we're seeing in that learning dexterity or other similar problems. So the first thing I want to point out is that this discontinuity with respect to velocity is a discontinuity in time. That is slightly different than the gradients that we are taking in an optimization problem. In particular, the question for gradient optimization of the parameters of some controller or some trajectory, that's about the continuity of solutions with respect to parameters, not with respect to time. So I want to shift the question a little bit, if gradient optimization is going to be successful, maybe we would like to have continuity in the parameters, okay? So instead of plotting as a function of time on the x-axis, my q's or my velocities, what I really care about is something else, some different sensitivity. Like if I change the initial conditions, so I'm writing that as q at t0, my positions at time 0, and I plot the final conditions after some finite duration of simulation, q at t final as my y-axis, and this is just a cartoon sketch, of course. The question is that smooth or is that discontinuous, right? And I'm using that sort of as these initial conditions plot here as kind of a surrogate for the dependence on policy parameters and other things. And I think if you work through it, I think you could believe that that's a reasonable surrogate. So if I change the policy parameters, it's going to change my conditions after the initial, or after the policy is taken into account, and then it will kind of evolve through the dynamics as if it was a change in conditions, in initial conditions. So this is a fundamental question. How discontinuous are our solutions with respect to the parameters or initial conditions? The continuity of solutions, from the mathematical model, if we ignore some of the numerical issues for now, is actually not as scary as you might think. So in this picture I showed before of the heel hitting the ground, we actually do expect that if I change the initial conditions continuously, then I would expect the final conditions, with f being my simulation function for some finite time, we'd expect q at t final to change continuously with the initial conditions, okay? The reason for that is through a chain of arguments, but the contact time changes continuously as I've changed my initial state. The pre and post contact velocities, they all vary continuously, and the gradients are all well maintained, and you would expect continuous solutions with respect to a continuous change in my initial conditions. Okay, now simulators have artifacts because they make discrete time approximations of all these events. And these, these do lead to discontinuities in our solutions. If you plot the simulation output exactly, unless you're very careful, you will see discontinuous solutions. We actually, in our simulation work, carry a burden of having both a continuous time model and a discrete time model, so that we can do variable step integration on a continuous time model and always try to do very accurate simulations so we can test our ideas and our results. But in practice, most of the performance simulation work is are with discrete time approximations. Now, those can be made small, but often we don't, because we want it to simulate at reasonable speeds. So we tend to choose fixed step solvers with large time steps, even though that leads to discontinuities. Now, the caveat there is the case I was talking about is when the contact sequence is known or fixed, because I had a point contact only interacting with the ground in the heel example. We do have real discontinuities in the mathematical model at the corner cases. So if I were to drop the heel or just some sphere on a corner of the box, okay, then there are discontinuous solutions there, of course, I guess, right? So if I were to plot this, if I change the initial position of the sphere, then at some point it's going to go left, on the left path of the box, and at some point it's going to discontinuously go down the right side of the box. Okay, and that's just real. I mean, you really do expect it to never end up in the center of the box, right? This happens when you make contact with a different face. If you have a mesh model, as soon as you make contact with a different face, you can get some of these discontinuities. It certainly happens when you transition to or from contact and no contact. So they're real discontinuities, but they're, I joke when I say more in the corner cases, but they are more about making or not making contact than about making contact along a surface. Now you might think, okay, what about soft contact models? That should make everything smooth. And of course it does. So if I were to make a smooth model of this sphere dropping on the corner, then it might rest exactly on the corner and very slowly change. But if you want those models to be reasonable and not allow too much penetration, then they're going to be very stiff models. So you see, I've drawn on the curve here. I might have replaced my true discontinuity with a very stiff, smooth approximation. But arguably, I'm not sure if it's stiff enough to be realistic. I'm not sure it's entirely different than having the real discontinuity. Depends on your numerics, but that's still a tough case. Okay, so that was point number one. Contact can lead to discontinuous or stiff dependence on the parameters, but primarily when you're making or breaking contact. Let's transition now to think about what optimization looks like given that observation. Okay, so if we have discontinuities at the corners, or from artifacts in our simulators, then maybe we can still do better by making the objective stochastic. If we do stochastic optimal control, that's a key idea from reinforcement learning, but from stochastic optimal control well before reinforcement learning. But I want to call out next that Monte Carlo with analytical gradients of discontinuous or stiff objectives can give bad results. This is a new understanding for me. It surprised me. I hope it will inform you. So let's think about non-smooth optimization. So if I do have some non-smoothness and I want to just take some arbitrary parameter x and minimize some function f of x, and that function is non-smooth, why does that matter? Why are we even talking about this? Well, gradient descent has beautiful theory and convergence results and lots of understanding for smooth objective functions. And it's well understood that non-smooth objective functions can throw a wrench in that. In particular, I mean, maybe obviously it can lead to introducing local minima. Maybe that's real and maybe that's okay. But I think more subtly, it can, non-smooth optimization landscapes can destroy the convergence properties of gradient descent or just make it behave weirdly, honestly, and mysteriously. So, a classical example is an L1 minimization where you can never converge potentially with a gradient update, a perfect gradient update. So there's a natural idea, which would be, can we just smooth out our objective function? And there's a natural way to write that in a probabilistic formulation, is if I could just think about turning this into a probabilistic optimization. So instead of minimizing with respect to x, f of x, I'll take, let's say, a little Gaussian distribution and drag it along x and ask about the expected value of f of x, given x was drawn from a Gaussian random variable. And now what I'm caring about is not the value of x, which is a random variable, but the mean of the distribution. And you can ask, what is the best place for the mean of my distribution to be in order to minimize the stochastic objective? Okay, that has a beautiful smoothing property. Okay, it's like taking a low pass filter in parameter space with a Gaussian kernel and just smoothing things right out. There's a lot of work in this world in optimization. It's often called randomized smoothing, in particular when you take this idea of the probabilistic interpretation of smoothing your function, and then you implement it numerically using Monte Carlo approximations. So if I draw some samples from that random distribution and I evaluate the function at a bunch of those points, how do I reconstruct the function or the derivative of that function? Okay, so a natural thing we would know would be that if we wanted to approximate the objective function directly, the expected value, we could take a Monte Carlo approximation. So I'll approximate the true expected value with drawing a number of samples and just summing those up. If those samples were drawn from the distribution, life should be good. Can you also approximate the gradient in that way? So the expected value of the gradient of the expected value, you'd like to think, well, the expected value is a linear operator. The gradient is a linear operator. I should be able to exchange them and bring them inside. And there's, with a little bit of algebra, you could easily derive for yourself this update. Okay. And this is maybe what we would expect to do if we were going to use analytical gradients. If our simulator had analytical gradients, we wanted to use them, wouldn't this be the right way to use them? There's a good, there's good literature on this. One example here is this paper on gradient sampling methods for non-smooth optimization. It's a recent version of an older topic. The answer is it's actually pretty subtle. Okay, so using a finite difference approximation of the gradient can sometimes be better than using analytical gradients when you're in the non-smooth world. Now that was, once I show you a couple of pictures, it'll be, I think, clear to you, but that I hadn't fully appreciated that until we started writing down these simple examples. So let me tell you that version. Here's the simplest example. It's the worst kind of example, and it's maybe too hard for the real robotics problems we have, but it'll make my case, okay? So imagine f of x is just the super simple function. It's +1 for x greater than or equal to 0, -1 for x less than 0. Okay, if I take a probability distribution and drag that along the x-axis and I ask what's the expected value, then it does a beautiful thing. It smooths out the objective, beautifully. So now the expected value of f of x under that Gaussian sampling, you'd expect in its closed form to be a beautiful, like, sigmoidal function. It goes through the origin, gradient defined beautifully everywhere. Okay. Now here's the trick. So if I were to take my Monte Carlo approximation using first order derivatives taken analytically from the original system, partial f partial x equals 0 almost everywhere. Maybe depending on how you define it, it's a delta function at the origin. Okay, talk about left and right sided derivatives, whatever but the fact is almost every sample you ever draw, with probability 1 is going to be 0. So any attempt to summarize the Monte Carlo statistics of that with analytical gradients is going to give you a total gradient of 0, whereas truly the gradient of the expected value is not 0. Yikes. Okay, so there is something subtle happening here where analytical gradients might not capture, since they're designed to capture the instantaneous effect. And there's a particular instantaneous effect with measure 0 that has a huge impact on the total expected value. You can just miss it if you're thinking about analytical gradients only. In practice, actually, first order approximations of this work fine. They're very robust to that, and they'll give good estimates. So what does that mean when I think about RL policy gradient or some of the covariant matrix adaptations or the planning people use for deep MPC, whether it's CEM or MPPI? Okay, we're often adding stochasticity into those problems, right? So I think the smoothing is happening, at least in the way we are formulating the problem. We get that smoothing not only from initial condition variation, but also from stochastic policies, from random initial conditions, some of the domain randomization. If you're just changing the shape of the objects that you're trying to manipulate, for instance, then you're going to get a similar smoothing behavior. The question is not the mathematical model, which I think is beautiful and has good gradients, but if you approximate that with Monte Carlo approximations, this is now a stochastic optimal control objective where you're trying to maximize the expected reward, just like we did in the last time. Okay, then this does smooth the discontinuous objectives that could come from contact. The question is, could a first order method do well, or are we stuck with zero order methods? Right? Why are people using zero order black box optimizations in these problems instead of first order analytical gradients? I've heard lots of smart people say, we should be using we know a lot about how to take derivatives through contact. Why aren't we using those in our optimizations? I think, I've said that myself, and I think it's pretty subtle, right? If we have a differentiable simulator, why shouldn't we be using it? And I think maybe that Heaviside example, although it's too simple and contrived in worst case, it should give you pause. Maybe it's not just as simple as taking analytical gradients and replacing our finite approximations. So there's a new line of thinking that we've been doing in my group. This is work by Terry Su and Tao Peng. So I think there's a beautiful way to think about these problems as through the lens of randomized smoothing. I think it starts to make connections between the type of algorithms we're seeing in RL and the approximations that we've seen from other smooth approximations of contact. And in particular, there's all kinds of good questions to ask. Like, if we now understand this is the source of the discontinuities, then can we reduce the sample complexity of RL by potentially sampling strategies that are targeting the specific non-smoothness that we're trying to address, if that's the real role that it's playing, okay? And I think it really sheds some light on potential relationship to some of the other smooth contact models people have introduced. Michael Poza, when we were working on contact implicit trajectory optimization, talked about relaxing complementarity constraints as Emo and Val have done stochastic complementarity formulations, and there's a bunch through there. Anatescu's relaxation for friction, I would say, fall in this category. And it's very interesting to think what role those are playing for smoothing, what role sampling can play, what's the optimal solution given all these potential candidates. I think we'll slowly distill this down to realizing there's only one or two key ideas hiding in there. So that was my second point. Stochastic optimal control can smooth discontinuous objectives, but Monte Carlo with analytical gradients of discontinuous or stiff objectives can give bad results. That surprised me, okay? It might explain some of the relative success of zero order methods. And I think there's new ways to think about some of these problems through the lens of randomized smoothing. Now, that's not to say that we should just rely on sampling to overcome all of the discontinuities in simulation. I told you there are some artifacts coming from our discrete time updates. I think there are other artifacts too coming from our geometry computations. And they can be subtle, but they can also be numerically subtle, but they can have devastating consequences for your simulation. And I have to wonder how much of our smoothing and sample complexity and all these things are coming from actually the fact that we're not simulating as well as we could be. So let me talk a little bit about hydroelastic contact models as a partial solution, a partial way to try to attack this problem. So in particular, this happened as for me, the awareness grew as I switched from thinking about simpler geometries of contact in walking to much richer geometries in contact in manipulation. Okay, so if I think about a dexterous hand, an allegro hand picking up a plate in a sink, by the way, this is a simulation. This is a nicely rendered simulation coming out of Drake, our open source solver. But if you think about compared to the point contact heel striking the half plane ground, now I've got a hugely complicated set of collision geometries that are interacting in very subtle ways with the plate, which is interacting in very subtle ways with the sink. And to get all that right and have it be numerically stable and good, and hopefully give good gradients, that's a big ask. So Drake is the website. I think the contact engine I'll tell you a little bit more details about the contact engine that's hiding inside there, and I think it's first class. So my claim is that subtle interactions between the collision and physics engines can cause artificial discontinuities. we shouldn't have to deal with these particular continuities, but because of our implementations, we often are. And sometimes they can cause to robots blowing up. I still remember when we were in the DARPA virtual competition playing with a simulated version of Atlas, walking over rough terrain, and our feet were shaking like crazy because of the contact simulation instability, or the time when maybe you've all experienced what we've experienced, right? So you have in that competition, we had to have our humanoid manipulate a hose. And at least a couple times in the actual competition, we had to have a rerun because the hose had some self-penetration and then ended up exploding out of the robot and knocking our robot backwards. And one of the hilarious things about the particular simulation tools we were using in the day is that they're using maximal coordinates. So your robot can actually literally explode. Your links can separate from each other going off in different directions. And it's disheartening when you're trying to win a simulation competition, but it's real. It's real artifacts, and we've all felt the pain. So let me tell you maybe how we can do a little better. Understanding this requires a few steps of logic here. Okay, so the first thing you have to appreciate is that when we have two collision geometries interacting, because of the numerical issues of discrete time approximations or soft contact models, we actually have to deal with the case of those bodies overlapping. It's not the case that you only have to think about surface on surface collisions. You have to think about what happens when two bodies have already overlapped and how do you get them out of contact, out of penetration, not just approaching penetration. The standard approach is to do this, summarize the forces required to separate two bodies that are in penetration with some small number of contact points and contact forces at those points. Okay, typically, sometimes even 1 point, typically a few points to get them out of penetration. I think it is effectively impossible to do this without introducing sometimes very severe discontinuities in your sensitivity to parameters. Okay, so let me just draw a few pictures to try to make that point. Imagine body A is just a box, body B is a box. Because of our discrete time simulation or my soft contact model, they've found themselves into some amount of penetration. The question is, what should the force be that my physics engine should apply in order to get them back out of penetration? You can also think of it as a constraint if you're doing a time stepping implicit formulation, but let's just think of it as a force for now. In both cases, they can be thought of as force. So I have to pick some point. If I'm only allowed to use 1 point, let's start with that case, then maybe I'll pick the point of maximal penetration, which, by the way, is already hard to define in some cases. It may be easy in this particular drawing, but there's cases where it's it's not unique to the maximal penetration point. And then what direction should the force act? Well, maybe I want to take it to the minimal exit wound, right? The closest point that gets out of the body. Or if I just want to minimize the length of that vector, maybe there's an ambiguity of solutions all along here would have been a perfectly reasonable choice. Okay, so the fact that we have to make that choice and the fact that that choice is ambiguous leads to all sorts of problems. Not just because I have to make this choice in one frame, but on the next frame I'm going to make the choice again. And if my algorithm is at all sensitive, or if there's multiple solutions or anything like this, if I get inconsistent choices between frames, then I can suddenly have very large contact forces and potentially exploding robots. Okay, so here's just a simulation that I'll use to build up of the particular point contact model we use in Drake. If we were to do nothing better than a single point, then we have a particular solution to the computational geometry problem that tries to minimize the length of that force vector. The green arrow is the force applied to the red box due to the overlap with the blue box. Okay, and you can see this is the box just being moved in a prescribed motion through the corner of the red box, and you can see that the contact force and the location it's being applied jumps discontinuously. Okay, this happens all the time. This is a careful example with exceeding amount of penetration for exaggeration, but it's really happening. Okay, so I would say that no matter how you choose to define it, I actually have a little interactive visualization I use in my teaching so people can pick any geometry A, any geometry B, start sliding them around, look at the force visualization, And you do that a little bit and you realize it's just a bad problem. It's like the wrong question to ask. Summarizing this geometry overlap with a single point contact, it's bad. Trying to summarize it with 2 contacts, 4 contacts, 10 contacts, there's no good number where I think you can get a sufficient stable simulation that works for all these contact geometries, right? In the particular approaches I've shown here, you might imagine that if my point of maximal penetration crosses the diagonal, then I can get a immediately discontinuous force. If I entered like this, I suddenly hit this diagonal, I get jettisoned out to the right or to the left of my screen. Okay, so this can make robots blow up. We have many heuristics for applying multiple points. The one that we find most when we're trying to do our sim to real work at TRI, we actually, instead of trying to embed heuristics that are opaque in the geometry engine, we have chosen instead to, in the collision geometries we're working on per scenario, to sometimes put in more simple collision geometries, like putting sphere contacts in the corner of boxes and then an inset box geometry on to capture everything else. That way we can ensure that we have stable contact locations, stable contact points. And that has been a big reason why we've had some better sim to real results, I believe, in very stable numerical simulations. But I think the real answer is to do better. And the real answer, the more general answer, is to think about not just trying to summarize penetrating bodies with a few points, but you just have to do a little bit more work and take the integral over a surface, okay? There's various ways to do that. The one we've proposed is called hydroelastic contact. It was originally called a pressure field model, but in Drake, you'll see it's called hydroelastic contact. It's available in the open source solver. The original authors, Ryan, Evan, Michael, and Sherm, and Andy, but there's been major contributions now from other members of the TRI team that have really made this work. Okay, so this is an example of a sphere just being driven up and down through a flat plate and then through a bowl. And you can see that there's a lot of computational geometry work, figuring out a total interactive mesh of the collision. And we're going to take a surface integral over the mesh and compute a complete contact wrench, so forces and torques, by integrating over the surface of that contact wrench. Okay, and you do that and you suddenly get beautiful stable simulations of pretty complicated things. So this is actually, the plate is interacting through its mesh contact on the rim of the plate. There's a sphere rolling on top of the ball. We can get fast, pretty fast simulations, not as fast as point contact, but fast enough to be very useful simulations with beautiful contact results. So if you look at the red vectors, these are our contact force vectors. And considering such a rich dynamics there, these are beautifully stable and good contact force vectors. People don't always draw their contact force vectors. Normally they're bouncing all over the place. We take pride in them being very stable. So this is what it looks like in the example I showed you before. When I have see the blue box is a bit thinner than the red box. So you'll see that as I drag it through, this is the case where the red box is considered to be completely rigid and the blue box is soft. So the surface of interaction that we have to calculate ends up being on the boundary of the red box. And we take an integral over this real-time computed mesh and we get a beautiful, stable contact force and wrench, which we can summarize the wrench drawing it anywhere. We choose to draw it at the centroid of the contact patch, and it's beautiful and stable and good. And the simulations come out a lot better. This is a case where both the red and blue boxes are soft, and then the contact surface that we compute is a compliant surface that sort of balances those stiffnesses and works in the interaction somewhere in the intersection. And just to make that point one more time, right? So remember, point contact bad, hydroelastic good. So hydroelastic is more expensive than point contact. It involves some expensive computational geometry in the collision engine, but I want to make sure it's clear that it's much less expensive than a finite element model. It's not doing a finite. So I think a lot of times when we talk about this, people say, well, do you really have to do finite elements? It's not a finite element model. There's a couple ways that it's different. So first of all, the geometry is assumed to be rigid and fixed. The geometry does not change shape. It's not summarizing the geometry with points that are moving. Therefore, there are no state variables associated with the surface. The state space, if you want to use for simulation, but also for planning and control, is still the original rigid body state space, okay? We are not modeling any of the deformation dynamics. We are just given an instantaneous frame of two bodies that are intersecting with fixed geometry, computing a force with a richer computation, okay? So we feel that it's if you think of point contact at one extreme of computational speed and multi-contact somewhere a little bit close to that, full finite element methods as being the slowest, possibly more accurate. We think of the hydroelastics as being our sort of Goldilocks position, somewhere in between the spectrum of computational speed and robustness and beautiful gradients. And it works on the full complicated simulation. So when you see our robot hand picking up the mug, you'll see that we're computing all of those mesh interactions in real time and getting beautiful, stable contact forces and contact interactions. Okay, so that's with the hand geometry removed, so you can see the mesh, but I hope that makes sense. And over and over again, we see results where that contact model has helped us get good results from simulations where the point contact model gave us finicky or bad performance. So this is just an example of a robot with a spatula picking up some food stuff from the table and then dumping it off. You see that I've made the collision geometries all transparent, so you can see the collision forces. Actually, Damrong made this video for me. Thank you, Damrong. And they're beautiful and smooth. And let me show you a couple of zoom ins here. So in fact, when we tried to take our little wedges of food stuff and simulate them with point contact, we had Mexican jumping bean kind of phenomenon. It was very unstable simulation and aphysical. And if we do the extra work to compute the real-time meshes of interaction between the food stuff and the table and the food stuff and the spatula, then we get beautiful, stable simulations, which we find is much more representative of the experiments we're doing in the real world. Just a couple other fun examples. So we simulated Legos, and we actually were able to simulate Legos accurately with manually curated point contacts, and you could simulate the mating. But boy, it's a lot of work to have to go through every new collision geometry and figure out where those contact points need to be. The hydroelastic does this standard computation, comes up with these rich contact geometries and beautiful stable contact forces, and to simulate two Lego bricks mating, and then being attached, and then you can pull them apart. It's great. Okay, so let me talk through how does that smooth things out in the corner cases. This is kind of a subtle thing. So on the point contact model, let me just drop a sphere at the corner. Thanks, Hankai, for making these videos. Then we'll just simulate a handful of different initial conditions as I moved this from left to right. I'll start that again. So as I move this from left to right, just a handful of different conditions of dropping a passive sphere towards the corner of the box. And it's showing you the simulator output. This is a continuous time simulation with variable step error controlled integration. So that's why it gets a little slower. It's in here, which is interesting. It's simulating the stiffness properly. And you get these discontinuous or very stiff solutions. And the hydroelastic has a richer geometry computation happening at the corners there. And you can simulate the same kind of effects, but you get this beautiful, smooth geometries, even through that diagonal is no longer some significant discontinuity waiting to strike. We're doing the rich computation. So the point contact has a discontinuity and the hydroelastic does not. So my message there was, be aware of artificial discontinuities due to subtle interactions between the collision and physics engine. And hydroelastic is one step, I think, towards finding the Goldilocks spot between a rich computation to give stable gradients, stable simulation without doing full finite element models. And I'll just end by saying, I talked a lot about continuity and gradients in contact with the hopes that would inform, help us think about the way gradient-based methods are solving these problems. But I don't think gradient-based trajectory optimization certainly gets us all the way there. I think we still need something more global, right? Smoothing a discontinuous function isn't enough. If we have these discontinuous landscapes, then we still have to reason about those different solutions at some point. So that means either clever parameterizations in the policy space, or RRT style sampling that does a more global optimization, or maybe when people are doing covariant matrix adaptation or CEM, some of the sampling, the global optimization aspects of the genetic algorithms are actually playing an important role, or something more needs to happen to explain, I think, the full richness of optimizing through contact. Now, for me, I think we can still do better right down understanding the physics without doing, generic smoothing. I think we can understand how to tessellate the space. We can understand how to write good global optimizations in this space, and then approximate them. The same way that AI is doing sort of discrete planning at the high level, and maybe we can do continuous control at the low level. I think there needs to be some role of deciding, am I going to go left or right around the tree? Am I going to pick up the coffee cup, or am I going to pick up the plate? Am I going to use my right hand, my left finger? And finding the balance between that discrete optimization and the continuous optimization is really a passion for me. So I'll just call out that there's some new work we've been doing that is the best we've done ever in terms of formulating these problems, the mixed continuous and discrete planning problems. The picture is very beautiful. I think it takes the idea of a graph search that we would do at the discrete level, and it pushes it down towards the continuous by saying, if I have a shortest path problem on a graph, and I have a directed graph and I want to find a shortest path, then we can generalize this by saying, every time I visit a point on the graph, I'm allowed to choose a continuous variable from a convex set, okay? And you get this problem of shortest paths on graphs of convex sets. It's a nice logical generalization of the original shortest path problem. It is harder in the computational sense, computational complexity sense, but it has really good approximations. And in practice, we're able to solve big planning through contact global optimization problems in fraction of the time we were solving before. And it's just, I'm very excited about the way it's helped us think through the problem in a different way. Okay, so my message for today is that, again, contact can lead to discontinuous or stiff dependence. Stochastic optimal control helps, but analytical gradients, you have to be careful. I think there's a new emerging story about how to blend all these tools together. Beware of some artificial discontinuities. Some discontinuities are real. Some of them might be almost bugs in the simulator. And I think you can do better. Hydroelastic has helped make our simulations a lot better. And we still need more global planning problems. Okay, that's my story for today. Let me just end by saying that I'm teaching this fall a manipulation class online, doing a lot of work to try to put the textbook online, the lectures online, even though we're back on campus finally this year. So if anybody's interested in following along or commenting on the notes, I'd be happy to hear your thoughts and get your feedback. Thanks very much.